Okay, so let's start the discussion of the 2023 MCQ paper. So question number one, electron volt is a unit of, well, this is quite easy. Electron volt is a unit of energy. Sorry, take this. Yeah. So electron volt is a unit of energy. It is basically, in simple terms, it's defined as the work done when a unit electron, or rather when an electron moves across a potential difference of 1 volt. So simply the idea is like this. If you have a potential difference of 1 volt like this, let's just say for example you have an electron, it's at zero gravitational, this is the zero gravitational potential line, so therefore it has 0 joules of gravitational potential energy, and also it's not moving. We placed a lone electron, a stationary electron, in this particular potential difference, so therefore the kinetic energy would also be 0. By the time it comes to here, it would have gained an energy of 1 electron volt, because this is 1 electron and it has moved across a potential difference of 1 volt. Electron volt has a magnitude of 1.6 into 10 to the power minus 19 joules. And you can see over here, this is actually quite easy to remember because this magnitude over here is actually the charge of an electron, because you know the charge of an electron is 1.6 into 10 to the power minus 19 coulombs. So it's quite easy to remember the magnitude of an electron volt. Now, I describe this as being work done, right? I want you to pause the video and think for a second, what is rather the sign of work done? You know, work done can be two types. You can have positive work done, you can have negative work done. When it comes to this scenario over here, what type of work done is this? If you guessed it as a negative work done, that is actually correct. Because over here, you actually have the field doing a work on the electron, and that is right. Okay, now I need to explain that too, because, okay, so what is potential, right? What is potential? So if I take a charge, if I take a positive charge like this, I can draw the field lines coming out like this. You can see it going out towards infinity. These are just imaginary lines that we draw for our convenience. These don't actually exist. So this is how a positive charge would be. Now, if I take a negative charge, it will be like this. You will have the field lines actually coming towards it, right? And if I keep any charge within these fields, if I keep it within the electric field of a positive charge, or I keep it within the electric field of a negative charge, you would have a potential acting on it. But this is just a potential, right? Because what I defined as electron volt being was that it had a potential difference, right? And what does a potential difference mean? Okay, so the easiest example that you can think of is when you take a cell. So this can be 0, this can be positive 5 or something, but this is not exclusive, right? Because this does not necessarily have to be 0, and this does not necessarily have to be positive 5. This could have been, well, right now it has a potential difference of 5 volts, but it could very well have been something like minus 10 volts and minus 5 volts, and you would still get a potential difference of 5 volts. But over here, we are talking about a motion of an electron as it moves through a potential difference. Now, as a physics student, you must know, okay, I mentioned in the very beginning that this electron, it does not have a potential energy. It is at the GPE equals 0, that means the ground level, almost, yeah, or sea level, 0 potential energy. And I also just placed it in the electric field, so therefore it has no kinetic energy. Now, for it to move through a potential difference, in order for something to move in physics, there needs to be a force acting on it, right? There needs to be a force acting on it. Therefore, it means that this potential difference, this is actually a potential difference, is due to an electric field. Because only if there was an electric field would it be able to exert a force on this electron over here. Because we know in physics that fields are basically certain, like an not electric field, but any field is an area that can exert a force on the respective particle. For example, a gravitational field can exert a force on a mass. An electric field can exert a force on a charge, whether it be positive, whether it be negative. Over here the electron is negative, right? So this over here corresponds, the delta V over here, the potential difference corresponds to an electric field. Now, I mentioned earlier that you can have a battery like this. You can have both of these poles as being negative, but it would still have a potential difference, right? But you can understand this is not the case over here, right? Because if it was to be able to move the electron from one point to another, you need to have an electric field. And an electric field in this case should consist of both a positive potential and a negative potential. Why is that? Because then you would have one side over here repelling the electron and the other side over here attracting the electron. You don't need to think too much into that, but I'm just saying logically for you all to get the feel of this, right? So that's exactly what's happening here. Now, in that case, we know, like I mentioned earlier, actually, I forgot to mention that when you have a positive charge, it would therefore have a positive potential. And if you have a negative charge, it would therefore have a negative potential, right? So therefore, in order for it to move an electron obviously is attracted to a positive particle, obviously a positive charge. Electron is repelled by a negative charge, therefore creating a negative potential in this area and a positive potential in this area. So you have an electric field that looks something like this. And then only you can be certain that when you place an electron over here, you would actually see a motion from this pole to this pole, right? Okay, good. Now let's move on to the equation side of this, right? Okay, let me just erase this up. Okay. So one of the things I didn't mention in the very beginning is although we consider electron volt as rather being a sort of, it's not a fundamental thing, but it's almost like the concept of a photon. We define something so that we can use it later on. But the truth is, electron volt is almost derived, even though it's defined as being something on its own, it's actually derived. And let me show you how. Okay, so it's like this. So you know how work done is equal to force into distance. And I mentioned in the very beginning that in order for an electron to move across any potential difference or for anything in physics to in fact move, there should be a force acting on it. And we know if there is electric field, there will be a force acting on this electron, right? And if you guys have done electric, electric fields, you would know that the force acting on an electron, this is mostly like this is a fundamental equation, is equal to F is equal to E Q, right? F is equal to E, actually this is capital E, this is electric field. F is equal to E Q. That is the equation on the of a force acting on a charge placed in an electric field. Okay, now let me show you something. Okay, so we have F is equal to E Q. Let me draw it as a capital Q. Now, when it comes to electric field intensity, we can write it out as this part over here. We can write it as E is equal to V over D, right? E is equal to V over D. This is actually the equation for when you have two capacitors, which is kind of like what I considered over here because it's easy to show it happening, like not two capacitors, but two, when you have two charge plates, just a single capacitor, but when you have two charged plates and this has a certain potential and this has a certain potential, the electric field intensity that will be within it is going to be equal to delta V, actually delta V over the distance apart. So you can see that if the delta V increases, the electric field intensity is going to increase. When the distance increases, it's going to decrease. That's quite logical. It makes sense, right? If you're going to be increasing the distance between the two plates, the two charges, or rather two potentials, are going to be further and further apart, and therefore you're going to end up with a lesser electric field intensity, right? Now, instead of E over here, I can substitute this and write F is equal to V over D into Q. Okay? But remember, I define electron volt as being an energy. It's a type of energy. It's a work done. It's a work done when you move an electron through a potential difference of 1 volts, right? It's rather the energy that that electron gains after it has moved through a potential difference of 1 volt. So I need to convert this into energy, and that can easily be done because this is work done. Energy is force in the distance, so all I have to do is multiply this side by D and this side also by D. So you can see D and D cancel, and instead of dF, which is basically F to D, I can write, let me take a different color, it's just getting confusing otherwise. I can write work done is equal to VQ. That's right. Work done is equal to VQ. Now you can see over here, remember in the very beginning I said that even though electron volt is something that we define as a standard, it is pretty much kind of like derived, right? So we can see over here is that if we in fact substitute this Q for an electron, we will get EV, which is exactly the equation, or in other words, even the definition of what an electron volt is, right? See, you can see it comes exactly as EV.